Next speaker, who needs no introduction, Dr. Peter Coveney from the University College London.
UQ, I don't like acronyms. That's meant to be uncertainty quantification. I'm actually on a sort of period at the Center for Advanced Studies at the Ludwig Maximilian Universität in Munich right now. So it's a very good thing to be able to come here from there. The last time I was at one of these meetings was in another distinguished German center, which was Göttingen. I think that was in about 2018. So what I'm going to talk about is what happens when you actually really want to understand the reliability of your simulations. There's a whole area of this. It's not just off-the-shelf methods that you can apply. I don't see anyone in this community applying them, but it's also a research area, and that is the one of uncertainty quantification. It's wider than that. It's really called VVUQ, which is validation, verification, and uncertainty quantification. I don't have time in this talk to go through what each of those mean in detail, but I want to look what happens if we consider free energy predictions, any other thing from molecular dynamics using these methods. And because I might get cut off by a zealous chairman here, I want to make sure I acknowledge people at the beginning rather than at the end. This is a set of people who've all collaborated with me. It's an underrepresentation. But I think perhaps today, if I can find it, and I'm not sure that I can see it on here, there should be a logo for the Insight Awards in the USA, because Insight is a way in which you can get access to the largest supercomputers that are available publicly, globally at the moment in the Department of Energy. And I'm going to talk to you about what happens when you use those machines. Because a lot of people in this conference, which is a fascinating combination of people from academia to industry and startup companies, are always trying to reduce the amount of computation they perform because they want to get a solution quickly but also very cheaply. Speed is of the essence here, of course. This is what I will try to race through. VVUQ is essential to be able to make actionable decisions. It means that not just you yourself believes the answer or have managed to get them published, but other people who depend on them critically will take it seriously. What's available to do it, how molecular dynamics fits in, what free energy predictions look like from that angle. And then I want to say something about AI solutions, because although I was just suggesting, and it's largely the case, that the micro world of atoms and molecules and electrons is rarely subjected to uncertainty quantification, artificial intelligence never is. And that's because it pleads for a form of exceptionalism that it must be right. But I suggest we make sure that we subject AI to the same rigorous standards that I'm trying to advocate here. The last one is about the recognition that this is a big enterprise. Digital twins is a buzzword that's now starting to hit the biomedical domain. And ultimately, it's about a virtual human that's a personalized one. That's an ambition. But it's in order to be able to predict things. And the National Academies of Science, Engineering, and Medicine in the US released a very interesting report on opportunities and challenges in digital twins in the middle of December last year. And I would strongly encourage you all to read it, because it includes molecular issues, of course, as they should be involved. But on almost every page there, you will see VVUQ, because in those domains, when it touches the FDA and the EMA and others, these are the bodies that will determine whether we can rely on these simulations or not. So this is just a quick look at the type of computers we actually use and have enjoyed. One of them is Superbook down in Garching in Munich, which is partly one of the reasons why I'm there. But you might see, look, I found out during the session on Monday when I was talking to one of the poster presenters, if he would just check on the website what's the status, because often at this time I would be at the International Supercomputing Conference that's every year held in Hamburg. And on Monday of that week, they announced the latest top 500. And the question has always been, will Aurora make it into the top 500 at a level that's respectable? In Denver last year, it came in at number 2, at 0.5 of an exaflops. Frontier's been there since 2022. It was announced in 2022 in ISC that it made the exascale level. This is supposed to be 2 times, but it came in at 1.01 exaflops, this one. So it's the second official exascale machine in the world. I say official because we have every reason to believe the Chinese do have ones, but they're not playing the Western game of entering their machines into this competition. But in any case, we've now got 2 exascale machines that we can use, and I'm just interested in making you think about what happens if you have such a large machine and you want to do complicated workflows and calculations. It's far easier to work with one machine than to try and wrestle with a cloud that may be here today and gone tomorrow and won't give you everything you want when you need it. But anyway, I will waste all my time with the background, but it's important to understand where all this is coming from. And weather forecasts are the example par excellence of what we mean by uncertainty quantification. And that's improved over many years, such that in today's top weather centers, which all have their own high-performance computing centers, they run typically around 50, you could call them in an ensemble, replicas of the simulation, with a lot of things being varied, especially the initial conditions. And I think we all know the reason why, and that's because the dynamics is chaotic. It's turbulent flow. And if you don't do that, and that's what the case was in weather forecasting about 30 years ago, you had very poor predictive value. But when you run a collection of these things, you get what we were hearing in the last talk, distributions. And that's what I'm most interested in. Distributions of free energies, for example, not just a one-off point and then inferring what the full system looks like. This is another example, very relevant, that struck us with COVID back in 2020 when the UK Prime Minister didn't like the idea of going into a lockdown, but he was being advised by some academic specialists in epidemiology, and one of them was Neil Ferguson, who's at Imperial College, and he adapted an influenza model in order to be able to predict the course of COVID from some initial inception here. And what his report with others provided to the Prime Minister at that point was this orange line. He ran one simulation, and that was what he was advising the Prime Minister about. And you can see this is deadly serious in more ways than one. It's the cumulative deaths predicted after the onset of the infection as a function of days. But what we're actually showing here, using some of the software and tools that we've developed to apply to any kind of computational problem, is this distribution. And that's what the uncertainty is like in this model, because all the parameters in this model, he didn't know how many parameters were in it when I asked him. And we were nervous about this because all of this type of stuff was going into the front pages of the newspapers. We're talking about predictions in biomedicine, which is a bit of a surprise, since mostly the biomedics only sort of want to believe something after they've seen it happen. But now everyone had to know what might happen as a scenario. It has so many parameters in it, and then you have to figure out which ones control the uncertainty. And I can't go into all the details of this, but this distribution is very interesting for a number of reasons. It's like others were saying, it's not a Gaussian distribution, it's got a fat tail on it, and it shows you how many deaths this model can accommodate when Neil Ferguson thought it was just down there. And this is the kind of thing we have to worry about if we're doing molecular dynamics simulations. So reproducibility is at the foundation of all of what I'm talking about here. We've got to be able to generate results that are robust and agreed by others. And it may be by the same means or by different means, and there are certain terms people use for them. So we know why we're doing this. And the uncertainties in uncertainty quantification come or stem from 2 different sources, and they use beautiful kind of philosophical Latinate language. The epistemic uncertainty is uncertainty caused by a lack of enough data to be sure of the problems, let's say the parameters in the problem and their values that might change. And so parameters here is what we're really looking at in uncertainty quantification. Whenever I have to deal with a problem like molecular dynamics, the first question I ask, like to Neil Ferguson, is how many parameters are you dealing with? Because I've got to figure out which ones matter from the uncertainty perspective. And then there's the aleatoric component, which has nothing to do with more data. It's whether the system is intrinsically, in the cases we're interested in, chaotic. And that means it will be sensitive to the initial condition you choose. And you better know how sensitive it is. And in fact, in that case, this is a nonlinear dynamical model. It's an individual-based rather than agent-based model, technical difficulty difference. But it's got lots of parameters in it. But as far as uncertainty is concerned, there are 4 random seeds in this problem, but in fact they contribute next to nothing to the uncertainty here. It's dominated by parametric uncertainty. And one of the other questions you can ask, and we have done and looked at for molecular dynamics, is how does the uncertainty that you feed in at the initial stage of the model propagate to the quantities of interest? That's a jargon term, but very handy in VVUQ. The quantity of interest here is the cumulative deaths. The quantity of interest in some of our other discussions is the free energy. How does that get propagated from uncertainty in the initial case? And you'd need to study and read the paper here, but it's inflated to the tune of 300% in this model. So if you don't know the parameters very well, when you make the prediction, you sure as hell can't be sure what the outcome is going to be. Have you thought about the uncertainty in a molecular dynamics simulation by comparison? So actually, a bit about software and stuff. I have to skate through this because I won't have enough time to deal with all that I want to talk about. But we have developed software. It's completely open. And at the moment, it's bankrolled in the UK by the Engineering and Physical Sciences Research Council. It's used deliberately to apply in any domain. And the irony of this is that I work quite heavily in the molecular domain, where virtually no one else is using these tools. But we develop the tools that are being used in many different areas now, including fusion, material science, weather and climate, and so on, because they're generic and actually quite easy to use. And you can get access to them through those websites. And really, it's just a matter in the end of being able to string together components that interface with each other such that this is the tool that you instrument your code with to set up a sampling regime and a kind of uncertainty quantification study, which might use stochastic collocation or polynomial chaos or one of those techniques, and then what the type of problem you're going to run and where you're going to run it. These things relate to the need to deploy the application wholesale on the machine, not just one run at a time, automation. And the pilot job manager, the most interesting part of this, because they unravel the whole application. It's like a Trojan horse. The system, in conventional HPC terms, wants to accelerate a job if it's very large number of nodes. So you con the system in thinking it's a monolithic application, wants a huge number of nodes. Once you've got inside the system, it unravels into a complicated workflow. So that's the structure of this thing called EasyVVUQ, and it really is quite simple to instrument your code. Of course, we've done it a fair number of times for MD codes, but many other things as well, and other people use it, and you can judge from their views of it rather than mine how easy it is to use. Coming to the molecular dynamics case, so basically it's the same problem, although for reasons I don't totally understand, this is hardly ever mentioned in these sorts of meetings or papers. Molecular dynamics is intrinsically chaotic, and it has to be, because if it's going to obey the second law of thermodynamics, the system has to reach an equilibrium in terms of the distribution function, not the trajectories. And the distribution function will only go to an equilibrium state in ergodic theory if that system is mixing, a mixing flow. And so we know if it's going to obey the second law, and after all, the free energy is a thermodynamic concept connected to the second law. That must be the case. We're going to have to deal with chaotic dynamics, and that's going to be probed by the sensitivity to the random seed you start with. But the basic picture you get is, if you're doing one of these biomolecular simulations, you run one of these simulations, you get one trajectory, you run it by some other method, or with a different initial condition, you get something else. And the one-off simulations typically are not reproducible at all, but if you can take them all together, then the thing becomes ensemble averaged into and that's what statistical mechanics is trying to do. The ensemble average is what you compute a macroscopic quantity from. So as people will know, and I don't have time to dwell on it, for example, one of the non-alchemical methods we've developed is using MMPBSA, but controlling the uncertainty through the aleatoric component of it, so running sufficient number of ensembles to get this thing to run reliably, and then you get what's not an accurate calculation, but a highly precise one, in the sense that it will rank the binding affinities, and it doesn't depend in any way on really on the nature of the molecule here. So it's not constrained in any perturbative way or in terms of charges and so on. And so this is one paper we put out here. Actually, this paper is it's kind of following the same route we did with Neil Ferguson's code that's called COVIDSIM down at the bottom. If you read that, you'll see that's what happens if you apply uncertainty quantification to the NAMD code. And in this case, again, how many parameters are there? Well, I'm not going to talk about the force field right now, but later in the talk, if I get enough time, I will. But without the force field parameters, there are typically around 170 parameters in an MD code. Most people aren't really aware of them, and they don't add up to much. But there are some others that do matter, and this is the result of doing an uncertainty quantification on the 12 or so parameters that looked the most of concern from sensitivity analysis. And it turns out here, and it's not really surprising that the temperature is the dominant one. This is actually showing what are called Sobolev indices that you get out of stochastic collocation, and they're the first order ones, because you can actually get second order ones as well. But basically, the larger this histogram, the more dominant its contribution to the uncertainty and the free energy. And you can see one or two other ones there, which include the box size and the compressibility are important. And all of this can be compressed into what are called P boxes and so on. I didn't hear anyone talk so far in this meeting about this weird discovery by Asthagiri and Beck, who are at Oak Ridge National Lab. But you may have noticed that they've discovered that if you run MD simulations with a time step greater than 0.5 of a femtosecond, you don't get any equipartition properly holding. And that does have ramifications for free energy calculations that people are doing by cutting corners substantially. Anyway, then there was discussion yesterday, I think it was, about non-Gaussian distributions, which we've been seeing for quite a while, because I repeat that if you run ensembles, you get lots of data, you build a distribution out of it, and then you can see what the free energy distribution looks like. So we made some predictions in a work we were doing with GSK, and I might show you those in a moment. But actually that made GSK colleagues have to go into the vaults of GSK in an area they don't normally work with, and they were very restricted by their masters in GSK to only divulge 2 or 3 of these things. But what these are free energy distributions measured for the important compounds, and these are the only things they measure a huge number of times. And this is an important point also, to determine the nature of your distribution, whether it's Gaussian or not. 3 points is nowhere near sufficient. These things are measured hundreds of times. And our simulations, I'll show you, need to run a large ensemble to detect this sort of thing. But it's very important, because if you want to know the expectation value of a quantity from molecular dynamics, it's not the maximum in the distribution anymore. There's a fat tail on it. It'll be heavily skewed towards that end of the distribution. So that's a picture. Last year, I discovered Journal of Chemical Information and Modeling had decided that they would now only accept papers which have 3 replicas in them. And that's like, with 3 I can calculate a mean and a standard distribution. This is like what people do in experiments, but it's nowhere near enough to determine convincingly whether these distributions are or are not Gaussian. This is just a paper they allowed us to publish there in reply to their suggestions, pointing out that if you really want to understand some of these properties, you have to do far more. And to the horror of many, look, up to 500 replicas in an ensemble, but when you're at that level, you can unambiguously tell that the skewness and the kurtosis are not zero, and therefore the thing is non-Gaussian. And so here's the thing about alchemical approaches, which fits nicely in here. We have this development which uses thermodynamic integration, and in fact, if you use this against FEP, you can do the same simulation and tag an FEP calculation on, you'll get almost exactly the same results. So the question is, who cares which way you do it? We find this to be a pretty good benchmark for all the work we do. And this is, again, on a large parallel computer. I can run everything at once because everything is so highly parallelized and independent. So if I'm working on an exascale machine, this is just chicken feed. But if it's on someone's local cluster, it's challenged to do one of these things. But that's the difference here. And so this is one point about FEP Plus that we discovered originally in 2018, but then we thought we better go back and do a really thorough study of what's going on with this. And the problem with FEP Plus, as we all know, is that it's proprietary and closed source, so you can't really identify all the problems in it. But what we have noted here, and this is published in the paper back in 2022, is that REST-2 isn't particularly reliable. It tends to take systems out of lower minima and populate higher minima as well. And that's a reason why some of the errors are proportional, in fact, to the uncertainty in the predictions. And you get problems with that with that running that code. And obviously also, Schrödinger's very keen on just running one simulation. And you remember what I said, I don't think that's a very reliable way of proceeding. This is just a comparison between the equilibrium stuff, let's say ties, and our interpretation of how one should do the non-equilibrium approach in a consistent way. And I say that because one of the problems in the literature is you read a paper and it's got a multitude of different replicas being used in different sets of calculations, so there's no consistency there. And then between papers, the difference is substantial. This isn't to point the finger at just this community. It's the same thing all over molecular dynamics. We have work on the glass transition temperature, which is in review at the moment, but we find people just running arbitrary numbers of MD simulations because they think that might help, but there's no systematics behind it. So this is just trying to say one thing that's very important here. Running a long simulation typically, as is advocated by people for the endpoints in this non-equilibrium approach, 40 nanoseconds is a long time. But you may or may not have already recognized that it's much more efficient in wall clock time to run a larger number of short simulations, only 5 nanoseconds. And that's because these trajectories are just going all over the place and sampling this phase space much more effectively than a single run will do. So this is why you can then renormalize this thing. It can be made to run in a shorter time frame, but it won't necessarily produce totally reliable results when it does. And there being so little time left, I will just talk quickly about the molecular dynamics side that I didn't touch on, the force field itself. This paper has just been published, and this is looking at how all the parameters in a force field affect the uncertainty of the quantity of interest, something people are always interested in. We know what the force fields are like, the amber one. It's got hundreds of parameters in it, and by conventional UQ, it's inaccessible. But we've developed some scalable methods to attack this problem. And this is materials with lamps, and this is free energy calculations with NAMD. And broadly, the interesting thing is that even when you average over the random seeds, you still have substantial uncertainty here. It's only when you average over the uncertainties in the force field parameters that this system is properly stable,
because it's so sensitive to the force field parameters. But what you can then do is actually perform what's called an active subspace reduction and end up, as this paper shows, being able to convince yourself that you've actually projected the dominant part of the uncertainty, as it were, into a one-dimensional subspace, one dimension, but it's like a principal component, linear superposition of all the most important terms. So I'm running out of time here, but these plots just show you which are the dominant terms that contribute to the uncertainty in the force field. And there's only, about 10 of those that make any difference. The rest of them are what you might call sloppy. And that's something you can do with uncertainty quantification with substantial resources available. And I think I will have to stop there because I'm under pressure. The conclusion from all of this is, if you want to do these things reliably, you have to be able to convince yourself that you're doing something reproducible. This digital twin technology that's coming to bear will make this even more imperative. As I said at the beginning, to do it properly, you need high fidelity models. You typically need rather large computers. Those the ones I mentioned earlier help a lot. And you need to think in probabilistic terms, together with uncertainty quantification. And I will just shamelessly plug my own book, which came out last year, about digital twins, that was published by Princeton University Press, if you're interested in it. Thank you very much indeed.
All right. Hi, Peter. Very nice talk. I felt the need to speak up just because I feel Schrodinger's view on this was mischaracterized. We've been advocating cycle closure correction since very early on in the development of free energy calculations, which is the equivalent of computing the same data point through multiple different pathways, which I think has nice conceptual analogy to your advocacy to compute something both with the Zwanzig relationship and with thermodynamic integration. The other thing I just might want to mention is there was a reply paper published to that study where there was apparent observation of bias, where we think there's a legitimate argument to be made that there was actually a bias in the analysis method that seemed to purport reporting of the bias, and some of your co-authors from that original study joined our reply paper. So I would just encourage anybody in the community interested in the characterization of bias. I think there's a very good dialogue in those two papers back and forth, going into all of the detailed questions that can come up when someone is chasing bias. So I would just say, from Schrodinger's perspective, very happy people are thinking about uncertainty quantification and how to calculate things through multiple different methods. So only just wanted to say there's no disagreement on that point, at least within our little corner of the community. So anyway, I just wanted to share support for that overarching goal.
When we're analyzing codes, we need to access them, we need to see what's inside them. And the idea of keeping...
Well, open source is different than bias. We can have that discussion later.
I'm sorry, if you're going to run a code that people have to believe, you need to know how it runs. And the second point is, if you noticed on Thursday of last week, AlphaFold 3 was released, and remarkably, that's also closed source. In the face of everything that nature says about making these things open, they have the audacity to publish something which is closed. I don't understand it.
Hello, I'm Greg. I'm from Isomorphic Labs.
Now, isn't that a surprise?
For all of those of you who applauded, you might want to know that it's going to be released open source in about 5 months, weights included.
Why would nature publish a paper that isn't open source? Its principles for everyone else are that you have to add everything in at source. Well, we read a paper which makes assertions that nobody knows to be true. And this is part of what goes on with AI as well. I didn't have time to deal with it. But if I ask how many parameters in AlphaFold 3, I don't know the answer, but that was my first question. But the answer is at the moment it has 10 to the 8 parameters in it, and I don't know how to do uncertainty quantification on such a problem.
The full methods of AlphaFold 3 are fully published. Users can access it right now, and it's going to be open sourced.
It can be open source. You're not missing my point. Nature has been making a big deal out of reproducibility. It ran a questionnaire in 2017 in which it famously found that
I'm sorry
70% of the people couldn't reproduce other work and 50% couldn't reproduce their own. We have a big problem here, and we need to sort it out.
I'm
Not
sorry
in
to
this sort of way.
cut this off. I'm sure it's a very wonderful discussion, but
It
we don't have time
definitely
for any more
is.
questions right now. We're going to move on to the next speaker. Thank you so much to our current speaker. Let's have another round of applause.